So welcome back, everyone. We are going to continue our discussion of supernova observables with the supernova neutrino signal today. I already walked you through the complications of neutrino detection and neutrino flavor conversion yesterday. So today, let's have a look at what the neutrino signal from a supernova really looks like. Go full screen, and what we can learn from it. So let's start with the overview first. So this is what the neutrino signal from a supernova looks like. On top, we have the luminosities split across 3 species. So the electron neutrinos and the electron antineutrinos. And here in these plots, we're lumping the heavy flavor neutrinos, nu X, into one species. That is done in many simulation codes currently. This is an approximation. In reality, the emission of the heavy flavor neutrinos and antineutrinos will be slightly different. And the emission of mu and tau neutrinos will also be slightly different. But to 0th order, the heavy flavor neutrinos, nu mu, nu tau, and their antiparticles are coming out with very similar luminosities and mean energies. The mean energies of the neutrinos as a function of time for different phases are plotted here in the bottom row. Yeah, so there's one phase that I've lumped in together here. So this is the bounce in the early accretion phase on the left. So what we see here is that we have this characteristic neutronisation burst, strong emission of electron neutrinos that I have already mentioned during the past 2 days. That dominates this early phase completely in terms of luminosity. Later on, the luminosities become more similar. We have somewhat higher nu E and nu E bar luminosities than nu X, nu mu, nu tau luminosities. In the later accretion phase, they may already become more similar. And once the explosion starts after shock revival, there's still an excess of nu E and nu E bar luminosity because you still have some accretion luminosity powering these other different from the heavy flavor neutrinos. Later on in the explosion phase, they become similar. All the flavors become similar, and their luminosities will decay over time scales of seconds. Yeah, and after time scales of seconds, here you see an actually more abrupt drop here. So after time scales of seconds, the neutron star will actually become transparent to neutrinos, and they can escape from the entire volume instead of just escaping from the neutrinosphere out of the trapped region. And then the decay accelerates here at the end. In terms of the neutrino mean energies of the spectrum, you'll find that generally the electron neutrinos are the lowest, except for this burst phase where they reach their highest energies. The electron antineutrinos are higher in mean energy, and the mu and tau neutrinos are highest at the beginning, but the electron neutrinos overtake them typically on longer time scales for some of the accretion phase. And once you get into the explosion phase, the rise of the mean energy stagnates, and eventually there's a decline of the neutrino mean energies, reflecting the cooling of the proto-neutron star. Okay. Now, what we'll do next is we'll go, after you may have some questions here, we'll go through the individual phases, understand better why the signal looks this particular way, and what we might be able to learn from that. So any questions up to now, or any leftover questions on neutrino detection and neutrino oscillations from yesterday? Nothing in the chat. Then let's have a look at the electron neutrino burst at the beginning. Yeah, so the physical origin of the burst has already been discussed. The burst base happens after the bounce when the prompt shock propagates into material of lower density. And once it reaches into material below densities of 10 to the 11 gram per cubic centimeter, then neutrinos produced there can immediately escape, and they will escape predominantly as electron neutrinos because you shock matter that's about symmetric with an electron fraction of 0.5, same number of neutrons and protons, and the beta equilibrium state, energetically more favorable state, is much lower YE. So the emission of electron neutrinos will immediately bring down the YE to hot beta equilibrium. Under these conditions, under these densities that may be of order 0.1, 0.15 initially, later the YE for beta equilibrium drops further. But the point is, in a significant region, a few tenths of a solar mass, you immediately jump from symmetric conditions, same number of neutrons and protons, to neutron-rich conditions by electron captures, and the neutrinos get out immediately. Now, one very nice thing about this electron neutrino burst is that although it looks a bit different in different neutrino transport codes, it is very uniform across progenitors. Yeah, that has to do ultimately with the fact that the central structure of the degenerate iron cores that form this proto-neutron star are very similar in their interior, and the neutrino processes during collapse may even conspire to make the cores, the collapsing cores, a bit more similar in terms of YE and entropy during collapse. So you get very similar conditions making the burst, regardless of whether you're talking about a high or low mass progenitor. And that, in a sense, makes the neutronization burst a potential standard candle. Yeah, so if you could measure the flux in a supernova detector, and you know what the actual structure of the burst is, you could pinpoint the distance to the supernova. This can be a bit tricky because, of course, the electron neutrinos, as I said yesterday, aren't what you primarily detect in Water-Cherenkov detectors. But even if you count on the lower count rates of the electron scattering channel in a Water-Cherenkov detector, you could still do distance measurements using the burst. And there are also, as I also said yesterday, there are detectors, the liquid argon detectors, that can detect the electron neutrinos, and you'll see how a burst will look in a detector like DUNE. One problem with that, of course, is that this depends really on the parameters for neutrino flavor conversion. So, for example, the mass hierarchy. And if the mass hierarchy is a normal one, you might actually not see the burst at all. That's a big problem. Or you'd rather see the heavy flavor emission there. That would not be so interesting. You could still use it as a timestamp. Yeah. But you can still learn something from it. I just got a question in the chat whether the uniformity of the burst is an assumption. Well, it's actually a prediction from simulation. So the simulations say that the burst is quite uniform. And of course, the simulations might still be wrong if the neutrino transport during this phase is wrong, or if the massive star progenitor models are very wrong. But this is, I would still say, one of the best understood parts of the supernova problem, where you don't have to deal so much with multidimensional fluid phenomena and flavor conversion, nonlinear flavor conversion, and so on. So I think this is one of the more robust predictions that we can actually make. Yeah. So even this rise, you see during this burst phase, the other the electron antineutrinos also rise slowly, and the muon tau neutrinos rise a bit earlier. So merely also pinpointing this rise of the other neutrino species other than the electron neutrinos is also helpful for timing the supernova dynamics. So this would allow you to put a timestamp on your gravitational wave signal, actually define where you ought to start your search for a signal in your gravitational wave detector. And if you looked very closely, you could actually do a little more with this signal here. So you could, depending on the shape of the rise of the signal in your detector, whether that's a little faster, what you see in the heavy flavor or electron antineutrino channel, you could use that to say something about the neutrino mass hierarchy, perhaps, or you could also constrain certain progenitor scenarios. For example, the flavor conversion during this burst phase would look a little different for this somewhat speculative electron capture supernova channel, because the MSW resonance region will not be adiabatic as the burst crosses it, because there's a very steep density gradient there. So there is some potential for the burst to learn, on the one hand, use it for pinpointing the distance and giving some absolute timestamp, but you might also learn some physics from it, both particle physics, something about the hierarchy, mass hierarchy, or about the progenitor structure. Now let's move on to the, before we move on, let's have a look at what the burst would look like in DUNE, which can detect electron neutrinos. You see here a bin signal where the structure, the temporal structure of the burst can actually be resolved. And you also see that it makes quite a difference that we have MSW flavor conversion, because if you took the raw signal with no oscillations, the burst would actually be a huge signal in the detector. And in the inverted hierarchy, you could still see it in DUNE. Yeah, so it would be this little blip thing here. Yeah, still a visible burst because of the lower survival probability of electron neutrinos. And in the normal hierarchy, you actually wouldn't see it at all. You would rather see the rise of the mu and tau neutrino emission. Now let's move on to the accretion phase, where really, well, you'll actually get much more counts from that phase in total in your detectors. And let's understand the structure of that signal and what you can learn from it. And to do that, let's review a bit more the neutrino interactions that are relevant in different parts of the post-rock region, and the equation of state regimes, because the physics that dictates the equation of state of the matter is to some extent also reflected in the neutrino interaction rates, and tells us what we must include in simulations and what we could learn from the neutrino signal if we detect it in case of a galactic supernova. So starting from outside, yeah, close to the shock, we have the gain region, yeah, outside the cooling region, outside the neutron star mantle, where there is, like in the gain region, convective overturn, and inside we have the proto-neutron star core. So in the gain region, that's where the the interesting dynamics is with regard to the explosion physics. Here we have net absorption of neutrinos, that make up for the heating. And this contributes little to the actually observed neutrino signal because we don't emit much. It will actually decrease the observed number flux or energy flux of the neutrinos by a few percent, what happens here in the gain region. So in the gain region where we're in a relatively simple and well understood equation of state regime, the pressure comes from non-degenerate electrons and positrons and from photons. The neutrinos interact primarily by charge current interactions and by neutral current scattering on nucleons. Mainly by actually little scattering. Sometimes there is absorption because that heats the material. And the nucleons that you interact with are non-interacting. That means the neutrino interactions here are quite simple. The heavy flavor neutrinos barely interact in this region at all. If you go deeper to where the neutrinos, most of the electron flavor neutrinos are produced, the cooling region, here both the charge current and scattering reactions are important for production of neutrino and for the production and transport of neutrinos. The equation of state here is dominated by the pressure of non-degenerate baryons, neutrons and protons, mostly neutrons, and a bit on top some contribution from leptons, which are sort of semi-degenerate. You have also some heavy flavor neutrinos coming through this region, from deeper inside. Remember, we already discussed the heavy flavor neutrinos are really produced deeper inside because at these densities, the interaction cross sections are still too small. But the heavy flavor neutrinos that go through here can still interact a bit. They can have, with a small probability, some interactions with this material, scattering of nucleons and transferring a little bit of recoil energy, or maybe breaking up light clusters. So they can transfer a little bit of energy into this region. They actually do. But in this region, they're not really produced. Now, if you go deeper to the neutron star mantle of densities above 10 to the 13 grams per cubic centimeter roundabout, you start to see interaction effects in the equation of state, somewhat. But they're still not really as pertinent as in the supranuclear density regime. The neutrinos of here in this mantle region, this is about where the decoupling of the new mu and nu tau neutrinos will happen. And here you can produce mu and tau neutrinos by various pair processes, electron-positron annihilation, Bremsstrahlung, and so on. And of course, there's always scattering that traps them. And at these densities, when you look at the charged and neutral current interactions that produce neutrinos or scatter them around, they start to be affected by in-medium effects. What do I mean by that? Maybe I'll make a little drawing. So somewhat similar to Bremsstrahlung, it starts to matter at very high densities whether your nucleon that you scatter on, so in vacuum, you might just have a neutrino that's a scattering of a nucleon here, and you can compute that using the tree-level amplitude from classical weak interaction theory. But at high densities, what starts to play a role is that the the nucleons actually interact strongly. And you have here various exchanges, various interactions, yeah, pion exchange or whatever, nuclear forces between the nucleons. And that will actually modify the interaction cross sections, both for charge current absorption and emission and for scattering. I'll come to questions in the chat shortly. Yeah. And at the highest densities, so in the proto-neutron star core, nuclear interactions dominate and dictate the equation of state. And here, the neutrinos are essentially close to thermal equilibrium with the matter, can be described by the diffusion equation. And what starts to be very important for the transport of neutrinos here is are these in medium effects, yeah, more so than they would be in the mantle region. And that now what that means is that on time scales, what all of this picture means really, what physics of the neutron star is responsible for shaping the neutrino signal depends somewhat on the times of the phases of the supernova that you're looking at. So over short time scales, where you can treat the neutrinos as trapped, nothing much is changing in the proto-neutron star core or even the proto-neutron star, the inner parts of the mantle. The neutrinos would basically come from the edge of the mantle. That's where most of the heavy flavor neutrinos come from. And a large part of them just comes from the cooling region. And for that reason, the high density in medium effects may not matter as much as they do in the later phase where the proto-neutron star is cooling and matter has time and the neutrinos have time to diffuse out. There, the in medium effects will have a much bigger impact than during the accretion phase. This is not to say that the in medium effects are negligible during the accretion phase. They actually do affect the game quite a bit, but not nearly as much as during the cooling phase. All right, we have a question here in the chat. The question is about what happens to the photons in the radiative zone. So you probably mean this radiative equilibrium zone here that I have in this figure. So consider the photons. The photons interact electromagnetically much more strongly than the neutrinos. So they are always trapped with the matter, basically. And you can just lump them into the equation of state. And there are no direct interactions that you need to take into account with the neutrinos. There is theoretically one process where photons play a role that can play a role in certain phases of stellar evolution and proto-neutron star evolution, which is the plasmon process for neutrino production, but that's not really of relevance here. Yeah, then the next question is there a preference for which flavor of neutrino is emitted? Yes, there is. As I showed you up here, yeah, there's simply a preference because some neutrinos can be emitted in this cooling region at lower densities, whereas others cannot. Yeah, but even let's say at the higher densities, the heavy flavor neutrinos and the electroneutrinos and antineutrinos still obey different interaction rates. Yeah. So until your conditions are hot enough for you to produce thermal muons, you will not produce any heavy flavor neutrinos by charge current interaction. Yeah. So the interaction processes of all of the neutrinos, species and flavors are different. Yeah. it's only, but they can still come out with very similar luminosities if they decouple in a similar region, yeah, because the luminosities that come out, in a sense, are dictated by the thermal conditions in the region of decoupling. So if the interaction rates give you a similar decoupling region, the emission will be similar, but the interaction rates are never completely the same. And some of these some differences persist throughout the evolution. Yeah. All right. And I should maybe talk a bit more about what this concept of radiative equilibrium here means. So basically, this means that this cooling region is relatively tightly coupled thermally by the absorption and emission of neutrinos from deeper layers to the outer parts of the mantle. That's what this concept of radiative equilibrium here really means. All right, so now let's, okay, and I have a slight typo in here, I see. Now let's discuss quantitatively how we can understand the neutrino emission. So as I said, the key difference is that the electron neutrinos and antineutrinos can be produced by charged current processes in the cooling region, whereas the heavy flavor neutrinos cannot. Yeah, and I think in one of the previous lectures I already hinted that you can describe effectively the heavy flavor neutrinos. Let's actually make a drawing to make this a bit nicer. Yeah, the heavy flavor neutrinos as coming from a neutrinosphere, the analog of the photosphere, further inside at higher densities, and you get from there a flux, which is 4 pi, disregarding relativistic effects, 4 pi r squared, the surface area, times the Stefan Boltzmann constant for neutrinos, which is a bit different from photons, times some factor epsilon, grayness factor, which takes into account that you don't have a black body, yeah, times t to the 4. That's a variation of the usual Stefan Boltzmann law for photons that you probably know, all of you. And the nu e and nu e bar neutrinos, they come from this cooling region, and they have an additional source of power, which is the accretion energy from the accretion flux into the gain region. Yeah, and that's proportional to the potential in the cooling region times the mass accretion rate. Yeah, and you can calibrate these relations based on simulations, and what turns out is that the emission of the heavy flavor neutrinos is actually not really a black body. It's a relatively gray emission, so much more inefficient than a black body, such that the grayness factor here is about 0.4, 0.6, and this the nu e's and nu e bars, they really add the accretion luminosity on top of a diffusive flux that can also be described by the Stefan Boltzmann law, and that means that you have a certain excess of the nu e and nu e bar luminosity over the heavy flavor luminosity. That's of order, yeah, so we can really say that's the averaged luminosity of one of these flavors is about that of the heavy flavor neutrinos, times a coefficient beta 1 about 1 plus the accretion luminosity, and the factor here, the beta 2 here, is also somewhat smaller than 1. It's of order of 0.5. Yeah, this first factor might be a little higher. So the gray body component for the nu E and nu E bar emission actually has a somewhat different grayness factor effectively than that of the heavy flavor neutrinos. Yeah. Now you'll see also if you look at the relative difference of the electron neutrinos and electron antineutrinos, their luminosities are quite similar. Yeah, the luminosities are quite similar. That might surprise you a bit because you'd expect that the neutron star, well, the proto-neutron star is still more proton rich than the final neutron star. So overall, it has to get rid of lepton number via electron antineutrinos. And it actually does that. So if you looked at the number luminosities, so the luminosity divided by the mean energy that you have here, you'd always have an excess of the electron neutrino number flux, but the energy flux is about the same. And that can be sort of understood by recognizing that in this region, where the cooling region where most of the electron and electron antineutrinos are emitted, these are very non-degenerate conditions and rather hot conditions. And that means that you have both many electrons and many positrons around, and the net emission processes can give you something with relative similar overall luminosity. Yeah, but you always have an excess of the electron neutrino number luminosity. Yeah. You also note that the electron antineutrinos always more energetic, have a harder spectrum than the electron neutrinos. That can be rationalized as well. We'll see about that in a second. And of course, something that's very interesting is that, well, you expect that the spectrum of the neutrinos and their mean energy really is essentially a thermometer for the conditions at the neutron star surface. And one can work out and verify using simulations that the electron antineutrino mean energy is a very good proxy for the neutron star surface temperature. And it actually happens to be related very closely with the mass of the neutron star. So you can sort of construct a model for the photospheric or neutrinospheric decoupling of the electron neutrinos. And the result is that the antineutrino mean energy is about proportional to the neutron star mass, which is relatively nice because that potentially allows you to constrain the neutron star mass as a function of time by measuring the electron neutrino emission. Okay, let's see whether I should go ahead with the next slide. Yeah, maybe I still go ahead with the next slide, and then we stop for questions briefly, because one finding that begs a question now is, of course, why are the electron antineutrinos more energetic than the electron neutrinos? That becomes quite obvious when you consider what their interaction rates are for absorption and emission. So the opacities will scale with the number density of the, so for absorption of electron neutrinos on neutrons, the opacity will scale with the neutron number density, and a phase space factor for a neutrino of energy epsilon. Yeah, and similarly for the electron antineutrinos, whose absorption channel is absorption by protons. Yeah. Now, two things are important here. One, if you have more neutrons around than protons, then automatically the opacities for the electron neutrinos will be higher. Yeah. Second, if you want to make a, if you want to absorb an electron neutrino on a neutron, in terms of the phase space available, that's much easier than absorbing an electron antineutrino on a proton. Why is it easier? Well, because the proton has less, the proton plus electron have less rest mass energy than the neutron. So this is an exothermic process, and the neutron decay by itself would be an exothermic process if you had the neutrino on the other side. Whereas you have to use up 1.29 MeV minus the electron rest mass in order to make a neutron from a proton by neutrino absorption. Yeah, and that means that the phase space factor for the interaction, the absorption of new E's is also bigger for the same neutrino energy than the phase space factor for absorption of new E bars. Yeah. So as a result, this means that the electron neutrinos have higher opacity, and that means that they actually decouple further outside. Now, this has one important consequence, because if you have a slight temperature, only a slight temperature gradient, yeah, in this cooling region, so if you have a slight temperature gradient in this cooling region, yeah, and the new E's decouple here, and the new E bars decouple here further inside due to higher opacity at higher temperature, then the mean energy of the electron neutrinos that will come out will reflect the hotter conditions here, and they will have a harder spectrum, higher mean energy. Yeah, and this is exactly what we see. Yeah, so that explains the harder spectrum, the hotter spectrum of the electron antineutrinos. In addition, there's another important effect. You see here in the cross sections, you effectively have a dependence on the neutrino energy squared. Yeah, and that means that the neutrinos of higher energy tend to decouple further outside than the neutrinos at lower density, at lower energy. Yeah, so neutrinos of higher energy are in contact, are thermalized and interact with the material even further out because the opacity is higher. And that means that, let's say, if you have neutrino energies E1 smaller than E2, then smaller than epsilon3, yeah, this means that the low energy neutrinos will originate in regions of higher temperature, and the high energy neutrinos will come out in regions of lower temperature, from regions of lower temperature. And that really means that compared to a Fermi, so if you consider the distribution function and you had a Fermi, or in the limit of vanishing degeneracy, Fermi distribution function at each point of the thermal production of the neutrinos, that means the higher energy neutrinos will be sensitive really to a thermal spectrum, reflect a thermal emission spectrum at lower temperature, and the low energies neutrinos will will reflect a thermal emission spectrum at higher temperatures. Maybe I should make the spectrum a bit less degenerate. Yeah. And of course, generally the neutrinos at coming from the spectrum at higher temperatures, the equilibrium spectrum at higher temperatures, that will generally imply higher neutrino intensities coming out from the inside there. Yeah. And the result of that is that the neutrino spectrum that emerges is really tilted or pinched with respect to a thermal neutrino spectrum. Yeah, because the low energy neutrinos actually come from hotter regions and the high energy neutrinos come from cooler regions. Yeah, so this is known as pinching. And if you're interested in the detector in inferring what the average mean energy of your neutrinos is and what the average cross section is, you need to be aware of this shape of the spectrum and parameterize this pinching accordingly. This is probably a good place to quickly stop for questions. Any questions there? Okay, let's proceed. So the spectrum formation of the heavy flavor neutrinos is even more difficult. And you can already guess that because you might think that since the mu and tau neutrinos have the lowest opacity, yeah, they do not interact by charged current, they come from higher density, and you would assume from higher temperature. But nonetheless, if you consider the mean energies, at some point, their mean energies drop below those of the electron antineutrinos. So that already suggests that the spectrum formation of the heavy flavor neutrinos is quite complicated. Yeah. So why is that the case? Well, the problem in understanding how the heavy flavor spectrum relates to the conditions, the thermodynamic conditions in their decoupling region, you have to take into account that they are produced at very high densities by various pair processes, but outside the region where their production freezes out, they can still scatter and exchange energy with the medium in scattering reactions. And this way you get down scattering effect. So the hot spectrum of mu and tau neutrinos at the production site, which is dictated by the emissivity in the Bremsstrahlung and pair processes, will be reshaped as these neutrinos pass through a scattering layer around their production region. Yeah, and they effectively downscatter, and their spectrum in terms of the average mean energy can become softer than that of the antineutrinos, electron antineutrinos. So this situation of the formation of the electron and electron antineutrino spectrum formation and the heavy flavor neutrino spectrum formation is summarized here, still in a somewhat simplified form because it does not take the energy dependence of the processes into account in this illustration from Raffel 2001. So the difference is with the electron flavor neutrinos, basically the emerging intensity is dictated by the thermal conditions at one region, the neutrinosphere of decoupling, where the optical depth is about 1 or 2/3. And for the heavy flavor neutrinos, the production processes freeze out much further inside than the surface of the last scattering, and their spectrum is shaped as much by the emission processes as by energy exchange reactions on their way from the production sphere to the effective surface of last scattering or transport sphere. Yeah. Now, what's the result of that? Yeah, the result is that all of these spectra will become non-thermal. Yeah, and as I said, that's quite important to consider for converting neutrino emission predictions from supernovae in supernova simulations into predictions for detector count rates, and vice versa for inferring from detector count rates anything about the flux, the actual physical flux and spectrum in the supernova if we actually happen to detect one. Yeah, this is especially important maybe for some detection channels that are sensitive to reactions with high absolute threshold values that really don't work below a certain neutrino energy density, or have at least high effective threshold values. So an example of a reaction with a high threshold value would be charge current interactions on lead in some smaller neutrino detectors. But even for, let's say, the inverse beta decay channel in Water-Cherenkov detectors, you have the dependence of the cross-section on epsilon squared. So the shape of the spectrum and any pinching of the spectrum will matter very much. Yeah. So modern neutrino transport codes can give you direct predictions of the spectrum, but for analytic modeling, or if you just have reduced data in hand, as someone who wants to work out possibilities, potential for a neutrino reactor, you might want to represent the neutrino spectra with simple fits, and you can use various ideas for that, modified Fermi-Dirac spectra, or even just something which is analytically very tractable, a generalized Boltzmann distribution, where the dependence of the flux on the energy has a general power law factor e to the alpha included, and basically depending on how much your spectrum is pinched compared to a Fermi-Dirac spectrum, this shape parameter alpha will take on different values. Yeah, and it's quite useful for many purposes, be it estimations of detection rates, or also post-processing of simulation data for nucleosynthesis, where you need the neutrino energy fluxes input to parameterize the spectrum using such simple shape factors. The big advantage is that these tend to be rather robust through these important big phases of the supernova neutrino signal. So here are a few ballpark numbers for the accretion phase, and those give you a rough estimate. All these pinching parameters tend to become a little more similar at later times, but the electron neutrinos always tend to be the most strongly pinched one, even if that pinching goes away later. They do become more similar to the electron neutrinos at later phases. Yeah, all right. Now, what can we actually learn from the neutrino signal? That's really the question that we want to answer. Yeah. Well, in principle, based on what I told you before, right, the neutrino luminosities as well as their mean energies are related to the neutron star surface temperature. They're related to the proto-neutron star radius, or rather the radius of the neutrino sphere, and they are related to accretion rate onto the neutron star. Yeah. So in principle, you could hope to disentangle these parameters by doing smart inference. Yeah. And combining time-dependent measures of the time-dependent data on the neutrino energy spectrum and their absolute flux with each other, and then reconstructing M and R and M dot as a function of time. In practice, though, because among other things, the question of flavor transformation, it's not that simple. And also you cannot so easily get reliable data for all neutrino, for the fluxes of all neutrino flavors. Yeah, but even in the light of these uncertainties, you can at least say something about the progenitor structure and maybe the final the neutron star that you make, because some of the emission features are actually quite robust. For example, if you consider the entire accretion phase here, where you have some excess of the electron neutrino and electron antineutrino emission over the mu tau neutrino emission, if you consider the entire phase of neutrino emission, both before and after the explosion, where the luminosities become more similar, still the overall emitted energy, which is the binding energy of the neutron star, is shared relatively equally between the different flavors. And that implies that if you can measure the total neutrino flux, regardless of flavor conversion, you can pinpoint the neutron star binding energy quite reasonably. The neutron star binding energy will be sensitive to the neutron star mass squared. That helps a little, this extra sensitivity, so that you can still pin down this important number by measuring the total emitted neutrino energy. If you go a little further and measure the electron antineutrino flux as a function of time, you may be able to pinpoint the progenitor structure, and specifically this compactness parameter, which I introduced in the first lecture to some degree. This might sound a little non-ambitious, but with really good time information and huge count rates for a galactic supernova, we will, I'm sure, with a good data analysis, be able to learn a lot on the progenitor and the neutron star properties. Once the data is there, people will work it out. And just to illustrate that, I mean, for supernova 1987A, we had about 24 neutrinos detected on Earth. And from those, we learned quite important lessons, yeah, that the binding energy that was emitted was of order 10 to the 53 ergs. The neutrinos came from a region of a few tens of kilometers in radius and had temperatures of a few MeV. So basically confirming the qualitative picture of core collapse and neutrino emission that I presented to you during this lecture. Now let's look at that concretely. So the progenitor dependence on really can be huge of the neutrino emission. So more compact progenitors, bigger cores, emit considerably more electron neutrinos and antineutrinos in particular. Yeah, you see that very clearly. There's easily a difference of more than a factor of 2 over the entire range of possible progenitor values in luminosity, and also an additional strong trend in neutrino mean energy, because these compact progenitors create more massive neutron stars with higher surface temperatures. That also helps, right? Because this will mean that these will actually make a lot more events in your detector because the spectra are harder. And even in the worst case, where you completely swap the electron flavor with the heavy flavor, you still see quite a strong progenitor dependence in the heavy flavor emission as well. And if you then translate this to a relation between the emitted energy in new E's during the first 500 seconds, what O'Connor and Ott found in this paper here, you see a strong systematic trend, and regardless of the nuclear equation of state, which will allow you to pin down, if you can do a good measurement of this emitted electron neutrino energy during the first few hundred milliseconds of the progenitor compactness. Good place to pause here for a second. Questions? Any questions? Well, then let me move on to something which is, I think, quite exciting, because you can actually use neutrinos not only as measures of these bulk parameters of the proto-neutron star and the accretion flow, you can actually detect, say something about the multidimensional fluid flow in the supernova interior. Why is that? Well, if you consider this standing accretion shock instability, where the shock sloshes back and forth or spirals around, you will get very asymmetric accretion onto the neutron star, and the neutrino emission in different directions will change all the time, periodically, reflecting these shock oscillations. And now the period of those oscillations tells you something about the shock radius. You can work that out. There's a relatively simple relationship. So if you can measure that time-dependent period, you can say something about the shock trajectory. And if the shock expands in this period, increases to sufficiently large values, you basically get an idea of when the explosion happens. And if for some reason after the explosion at some point you still have matter falling back onto the neutron star and raising the neutrino emission again, you can also see that. So this scenario is depicted here. Yeah. So the idea is that shock oscillations will modulate the neutrino flux, where there's shock retraction and more accretion, you get enhanced neutrino emission. And this thing here will wobble back and forth all the time. So if you do a simulated signal, calculate a simulated signal of that in the ice cube detector, that looks like this. Does look quite a bit noisy, but you see this noise is actually a real signal. Yeah. And you then see, if you go into the time frequency domain, you see a clear signal that during this phase here, you had this standing accretion shock instability. And I show you here this red curve depicting this analytic relation, which fits the actual signal very well. Yeah. So if you see some structures like this in your signal, you can actually say, I had a shock here at this time with that radius, this and that radius. All right. Yeah, and if you have events like fallback later on during the explosion, so this is an example from an older 2D simulation. Yeah, here we have in orange an expanding neutrino bubble, and there's a downflow in blue and black coming in here, and it penetrates through that bubble and hits the neutron star. Then you might get occasional small bursts of neutrino emission. Yeah, in your detector, if you have sufficiently high count rates to have good time resolution, like in Hyper-K or IceCube. And if you detect something like that, then you can say that gives you a hint that there was perhaps something like late fallback happening in your supernova explosion. Yeah. Some of these signals can be a bit ambiguous, and I'm bringing this up also because someone asked about this scenario yesterday. So for example, it has been speculated that, well, you could have a first order phase transition when you get to sufficiently high densities, a first order phase transition to quark matter, and that could lead to a second collapse of the neutron star and launching another shock wave from the rebound of that second collapse, and that would then make another neutrino burst. In this case, people worked out that it would actually be an anti-neutrino burst, which is interesting. Very short, very spiky. So if you detect something like that and can somehow distinguish it from fallback accretion, which you might, because fallback accretion will probably leave you at a plateau with higher emission afterwards, and it would give you a signal that's probably not as sharp as the one from a second bounce. Then you might use that as a smoking gun for something like a first order phase transition. But one has to bear in mind that the parameter space for phase transitions have shrunk since this work was first published. We have much more stringent constraints on neutron star masses and radii these days. So accommodating this scenario has become a little more difficult, though not impossible. And it might be more restricted and happen only for very, very massive neutron stars. So this was an overview of what you can learn from the neutrino emission in a supernova. There are more things, and I can't cover all of those. If you are interested, I encourage you to read reviews that I mentioned and the papers cited within them. So you could learn from the neutrino signal, from the cooling phase, something about the physics of the equation of stated high densities. Yeah. So for example, then the nuclear symmetry energy will affect how the cooling signal, the late cooling signal after the explosion unfolds. You could constrain neutrino physics parameters or other particle physics parameters, so put better constraints than we have now on axion emission and so on. Yeah, so there's a lot of things that you could actually, a lot of physics potential of neutrino detection beyond just constraining supernova dynamics. And I've just given you a first glimpse into that. Yes, good. So that's as much as I wanted to say about the supernova neutrino signal. And we can have more questions here before we start talking about the nucleosynthesis in massive stars and core collapse supernovae. Questions? No questions at this point in the chat? Don't hesitate. I realize you've been exposed to a lot of new knowledge here. So I see that was probably a bit overwhelming and tiring. So don't hesitate to ask questions now or later. Yeah, but if there are no questions now at this point, let's just move on and talk a bit about the nucleosynthesis in massive stars. Yeah. So we've already gone last time, or in the first lecture, through, well, basically what kind of nucleosynthesis stages occur in massive stars and what the structure is that the massive stars evolve to. Yeah, an onion shell structure where you have at the end, iron in the core, silicon, sulfur burning shell around it, then oxygen, then an oxygen neon magnesium shell, a carbon oxygen shell, a helium shell, and a hydrogen shell. All of that's not to scale here. Yeah. So with that, you already know what the main products of nuclear burning are. In massive stars, the supernova will do a bit with that, a bit more with that. We'll discuss that, and we'll also just look a bit in more detail in what any other side products of these burning stages would be, and understand the physics of the individual burning stages a bit more. Yeah, and we'll start relatively, hello, question? And we'll start with relatively basic things, relatively early in stellar evolution. So hopefully picking up on something that you probably know, which is the physics of helium burning. Yeah. So after core hydrogen burning, the next thing that you ignite in the core is helium burning. And helium burning is effectively really a 3-particle reaction. Yeah. So what happens is you could fuse helium, 2 helium-4s into beryllium-8. Beryllium-8 is unstable, so it stays around only for a very short time frame. And if within that lifetime you can capture another helium-4, you make carbon-12, followed by a gamma decay. It's actually essential here that there's a resonance in carbon-12 at the exact right energy for this reaction to be able to happen. Yeah. And yeah, you'll get an energy generation rate that has already a much steeper temperature dependence than hydrogen burning and dependence on density squared. Now, one interesting thing to note about helium burning is that it unfolds slightly differently in low mass stars and high mass stars. Yeah, in terms of the weight of the end of the final products. Because what you can also do during helium burning, if you have carbon-12 as one of the fusion products, and you have lots of helium around, you can actually do alpha captures on carbon-12 as well. So helium burning doesn't only make carbon from the triple alpha reaction. If it happens under the right conditions, where there's actually a lot of where the temperatures are high enough to allow this extra capture reaction, then it will make quite some oxygen as well, and it could even make some neon. Yeah. And if you compare the burning conditions in high mass stars and low mass stars, you find that the conditions in high mass stars are actually more favorable to making oxygen by a second capture. And this is already one of the reasons why the massive stars, in terms of their overall contribution to the chemical inventory of the galaxy, contribute more oxygen than the low mass stars. Most of the oxygen in our universe comes from burning in high mass stars. Yep. So then once we've made carbon, what happens with that? Well, the carbon burns by still very much a, okay. Okay. This is actually one important thing here before the carbon burning. Yeah. So one important thing that also happens during helium burning already is that, well, if you know something about hydrogen burning in massive stars, you know that this goes primarily through the CNO cycle, at least at solar metallicity. And the lighter nuclei, CNO nuclei, are all shuffled into nitrogen 14 after CNO burning. Yeah. Now, this nitrogen-14 will then be consumed during helium burning and can do further reactions and go to oxygen-18. Yeah. And this oxygen-18 that you make there is important because that introduces into the fusion products that you carry along during the further evolution as a small neutron excess. Yeah, so you will destroy that later by capturing on oxygen-18, capturing an alpha and making neon 22, but the neutron excess is retained. I should probably say at this stage here, does anyone need an explanation of what this notation of nuclear burning reactions is? I suppose people might need a comment on that. Yes, yeah. Mm-hmm. So in longhand, you will write, you're used to writing nuclear reactions as something like this, right? So let's say C12 plus alpha goes to oxygen-16 plus gamma. Now, we don't want to write in nuclear astrophysics, we don't want to write arrows all the time. So we use a shorthand notation where we have the heavy particles, the nuclei outside brackets. So this is the fuel, and these are the products here. And any light particles that go in or go out are put into brackets. So this means carbon 12 plus alpha helium going in will go to oxygen 16 and a gamma going out. Yeah, that's what this notation means. All right. Yeah, good. Okay, yeah. So as I said, this is an important side effect of helium burning, that you convert the nitrogen-14 into oxygen-18 and imprint a neutron excess on the material that's carried along during further reactions. Yeah, so this will happen later. So what you can later do with this neon 22, you can liberate that neutron again by an alpha capture, and then you can use those neutrons to make a slow neutron capture process. So catch those neutrons on iron group nuclei and make neutron-rich nuclei heavier than iron. Yeah, and this will lead to a slow neutron capture process in massive stars. Works with fewer neutron or smaller neutron fluxes than in low mass stars here, and therefore it will only make these S process isotopes up to mass numbers of A equals 90. We'll see in as a function of nuclear atomic number later on where the elements produced in massive stars, how these actually cover the entire landscape of the nuclear chart. Yeah, but this is something to be borne in mind later. So we make during helium burning, we get some neutron excess of the material, and that will be used, or that will lead to some form of S process, the so-called weak S process in massive stars later on. Now, when we go on to the next burnings, yeah, we've already discussed their physics quite a bit. So this is something that almost exclusively happens in massive stars. The carbon burning might still occur at the transition region from low mass stars to high mass stars, yeah, where you're close to the threshold for ion core formation, but don't get there and instead make an oxygen neon magnesium white dwarf, but mostly it's limited to massive stars. Yeah, so during these burning stages, we already know the physics. So you'll get the the dynamics of the burning will be dictated by this state of balanced power. You primarily cool these phases by neutrinos, and the balance of balanced power basically fixes the burning temperatures to relatively robust values. So let's look at these burnings. The first is carbon burning. So carbon burning it starts to be a little more complicated than helium burning because all these reactions of the more massive nuclei tend to have more kind of branching reactions, and the number of isotopes, less important isotopes, less abundant isotopes that you make gets bigger and a little more difficult to keep track of. But primarily the carbon burning makes magnesium, so it changes the carbon into magnesium and neon. Yeah. It does also make a few isotopes that are a bit more massive, and the oxygen is basically conserved during this phase, right? So nothing much happening with the oxygen, and that's simply because the oxygen, as a more highly charged nucleus, of course, has higher threshold energies for reactions. All right. Then what happens next after carbon burning? The next thing that happens is neon burning. And neon burning is now different to carbon burning in that it's actually a photodisintegration reaction. So you don't make directly more massive nuclei. Indirectly you do. So what happens at about 1.5 gigakelvin is that temperatures become high enough to knock out an alpha from neon 20 and convert it back into oxygen 16. But these alphas, of course, can also do capture reactions. So if the alphas are captured by the neon 20, you make more magnesium 24 as well. Yeah. There are also a few side products, some aluminium, silicon, and phosphorus, but primarily what you do after neon burning, you convert the neon that you have from carbon burning, you convert that into oxygen and magnesium. Goes on, yeah, oxygen burning, you need somewhat higher temperatures and the hydrostatic conditions about 2 gigakelvin, and oxygen burning in terms of the product starts to be more complex because of the many secondary reactions. Yeah, so you produce everything from silicon, sulfur, and up in further up with somewhat lower abundances, intermediate mass elements like chlorine, argon, potassium, and calcium, and so on. Yeah, the massive stars are the primary producers of these elements in terms of their contribution to the galactic inventory. For calcium, thermonuclear explosions also contribute quite a bit. Yeah, then it gets more complex yet with silicon burning, and silicon burning is now of a completely different nature. This is something that's probably not so much discussed in textbooks, because silicon burning, starting from about 3.5 gigakelvin, does not really happen by two-particle reactions of heavy nuclei anymore. Oxygen burning still does, yeah? So you throw oxygen nuclei at each other and they react. With silicon, that's no longer the case. The net reaction might be that you start with silicon and you end with nickel 56, but the actual physics is more complicated, yeah? The way silicon is converted to ion group stuff is really the following. So the higher the temperatures get, the more alpha particles you liberate. And then with those alpha particles, you make a chain of reactions. Yeah. So an alpha capture on silicon 28 gets to sulfur, and another alpha capture gets you to argon 36, and so on and on to the ion group. Yeah. And this is not a one-sided reactions. The alphas can also be knocked out by gammas, and you get into an equilibrium state. And the equilibrium state really depends on how many alphas are around. Yeah. So in a sense, you can view the change in composition as a result of silicon melting, the fuel silicon melting more and more into alpha particles. Yeah. And in this equilibrium chain, the abundances of the various elements and various isotopes will be given by an equilibrium condition. So not a thermal equilibrium, but a partial equilibrium for alpha captures in this chain. Yeah. So you will get what is essentially a Saha equation. So aside from Chandrasekhar, we're now coming across another famous Indian physicist, this time in the context of nuclear reactions. Yeah. And that's what dictates the nature and outcomes of silicon burning. Yeah. So it's really not the important takeaway for you, this is just good background knowledge, is that silicon burning is not that two-particle reaction that we're familiar with from earlier burning stages. It's you slowly transition to a more, you have an equilibrium distribution of nuclei mediated by alpha captures and alpha emission. And the more alphas you have, the more this will shift actually to the ion group. Yeah. And it's, yeah, so during this time also, if you have sufficient time for weak interaction processes to play a role, what can also happen is that what will happen is the matter will deleptonize. So you will have beta decays and electron captures that will drive the products of silicon burning to a more neutron-rich state, and that can end you up as iron 56 instead of nickel 56, which you would get if you had just strong and electromagnetic interactions. Yeah. One important thing to also note about silicon burning is that the products of silicon burning in the progenitor will mostly stay locked up in the progenitor. Yeah, this is the region that will go into the proto-neutron star, and the products of silicon burning will really just be products of silicon burning that occurs during the explosion and not during the progenitor hydrostatic burning phases. All right. Yeah, so a brief summary of what you get from massive stars up to the point of core collapse. Yeah, so you're left with helium. You get some helium from the hydrogen burning. You've reshuffled carbon and oxygen in the CNO cycle to nitrogen. In the shells that have undergone helium burning, you make mostly carbon and quite some oxygen in massive stars. From carbon burning, you get primarily neon and magnesium and a few of the other ones in that vicinity. More oxygen and magnesium from neon burning, then intermediate mass elements from oxygen burning, and most of what you make from silicon burning will actually later on be locked in the neutron star. And I hinted at from the neutron excess isotopes that you have in between, you can make some you can liberate some neutrons again and make some slow neutron capture process elements. You'll see that later on in the overall production factors that I'm going to show you. And in the interest of time, I should probably at this point, because we have to break here somewhere, skip ahead a little. Oh, how did these get out? So for some reason, these yield patterns aren't there in the lecture. That's strange. Something has happened to the PDF. Okay, I'll show you that tomorrow then. Yes. Yeah.
Bernhard, when you say low mass and high mass, is there a indicative value where we...
Yeah, by low mass and high mass, I now just mean low mass is everything that doesn't make a core collapse supernova, and high mass is everything that makes a core collapse supernova. So starting from about 8 or 9 solar masses on the main sequence for single stars.
Can I ask a question?
Yes. Mm-hmm.
From what I remember, the Saha equation is only applicable for things in equilibrium, but I might be completely wrong.
Mm-hmm.
Is that a good approximation here?
Yes, you are right. It's so the thing about the Saha equation, it's applicable if any of these of the reactions that you apply it to are in equilibrium. Yeah, then you can apply between those stages the Saha equation. Yeah, what you don't need is you don't need a complete equilibrium, so you don't need the magnesium here to be in equilibrium with any reactions that build and destroy it from alpha particles. Yeah. Right. What you'd have to do then is you have to include your alpha mass fraction as an independent variable in this whole game. Yeah. And the alpha mass fraction can also change. Yeah, so it will be essentially a parameter that dictates the Saha equilibrium between these heavy nuclei. Yeah, so short answer, you can apply the Saha equation to the reactions that are in equilibrium. And if you have particles that are not in complete equilibrium with all possible reactions, you just need to add those appropriately as factors. Yeah, and solve extra rate equations for them.
Okay.
Any other question?
Yeah, hey Bernhard. So how do we observationally? How did we learn all these things about the exact nuclear burning and all these things? Is it a set of different types of observations, or is it mostly absorption lines and those kind of things from during the supernova? Mm-hmm.
Yeah, ultimately, this is actually a very good question. How do we know about this observationally? There are 2 sources of information. So one is you can look at the abundance of stars in the observable universe. Yeah, so the stars that are just around and have been formed from supernova ashes, yeah, like our sun, yeah. And then you can interpret the abundances there from solar observations, from meteoritic abundances, and from observations of stellar lines, also across galactic history, and piece together whether that fits with our picture of how nucleosynthesis works in massive stars and low mass stars, whether we make enough of each of those elements to explain those abundances. That's what you do through this approach of chemogalactic evolution modeling. So that's one approach, and there you can just say things fit. Yeah, it's not a proof that the supernovae are doing exactly what our models say they do. Then you can look at the supernova itself. Yeah. And observe lines there and attempt to quantify the amount of material they make. Quantifying exact mass fractions, or very exact mass fractions, is somewhat difficult, but you can especially from spectra of the late phase of the supernova light curve, the so-called nebular phase where you're dominated by emission, and from supernova remnants, you can measure things like the overall mass of oxygen that certain supernovae produce. From the light curves, you can measure how much nickel-56 they produce, which of course will not come from from the pre-supernova nucleosynthesis. The nickel 656 is all made during the explosion. You can yes, so you can use that to infer and quantify some production that happens definitely in a massive star that exploded, either coming from a pre-supernova evolution or from the explosion itself. And that at least tells us that our understanding of massive stars making a lot of oxygen, that's correct. Yeah. So both of these kinds of observations complement each other, and neither is perfect on its own. Yeah. Yes. Then you also have things like additional information on massive star nucleosynthesis, for example, from background gamma emission of aluminium-26. Yeah, you can use that as an additional constraint. Yeah, so you have to piece together many sources of information on nuclear abundances and check whether that fits the overall picture.
Yeah, thanks a lot.
Any other question for Bernhard before he has to leave, as he said today? So last chance to ask your questions.
So I have a question. Okay, in short, what I wanted to ask was, how are these reaction chains actually modeled in these massive star simulations? Is there like a fine-grained description where you won't have to resolve, you know?
Yeah, that's actually a very good question. So this is done slightly differently in stellar evolution codes and in supernova simulations. So in the best modern stellar evolution calculations, what you do is concurrently with the stellar evolution structure equations, you solve huge networks, hundreds to thousands of nuclei, yeah, and model the reactions in detail. Yeah. In the supernova simulations, what you usually do is you put in a small network or an even simpler treatment which will get the most important reactions right that are of relevance for the energy budget. And then you take your simulation data, you post-process, you extract trajectories of tracer particles that moved along with the flow. And then you solve, again, huge reaction networks based on the thermodynamic trajectories of the ejected material and assemble the nuclear yields based on that. Yeah. Does that answer your question?
It's not like a coarse-grained description in the supernova simulations, is it? It's just lesser number of reactions being modeled. Yeah,
so there's a variety of approaches, really. So some supernova simulations don't care very much about the nuclear reactions. They might care as little as saying, at some point I'm getting into, at low temperatures I have a certain composition, at another high temperature I have nuclear statistical equilibrium, and everything changes to whatever nuclear statistical equilibrium is, and no more detailed description than that. So you could probably call that coarse-grained, I guess. Yeah. And some supernova simulations already have rather, moderately sized networks of 20 nuclear species or above that.
Anything for Bernhard? Okay, if there are no further questions, so let's just end the session for today. Thanks, Bernhard.
Thank you very much. So what we're going to do tomorrow is I'll tell you more about the nucleosynthesis that happens during the supernova explosion, and then how everything is pieced together, and a bit more about supernova phenomenology. Yes.
Thank you.
Yeah, and have fun with the tutorials. You're going to have the opportunity to play with a nuclear reaction network to a bit more intuitively understand some of these things as well, if you haven't done it already.